Section 1.6 is on continuity. So continuity comes right after limits. And if you remember when we were talking about limits, we did mention the word continuity. So why do we care about when a function is continuous, or what is continuity? Well, the idea was with evaluating limits, we realized that sometimes you could plug the number directly into the function, and sometimes you needed to use other techniques like looking at the graph, using a table. We used factoring and simplifying, multiplying by the conjugate. So there were the nice occasions where you could just plug the number in, and then there was the not so nice occasions when you had to do something else. Well, those nice occasions when you can actually plug it in, that is when a function is continuous. So as long as a function is continuous, to evaluate the limit, all you have to do is plug in the given x value. You don't need to use a table. You don't need to use the graph. You don't need any other techniques. Just simply plug it in. So continuity is really important for us. They're the quote-unquote nice functions that we want to see. So what makes a function nice? Well, this is a wonderful graphic on this page that really explains what it means to make a function nice or continuous. There's really primarily three things that can go wrong when you're looking at a continuous function. So we got to keep in the back of our mind, when can we just plug in the value, and that is the actual limit. So let's look at x equals c1 on this graph. The first thing that you notice is there's an open circle where f of x should be defined, or f of c1 would be defined. That open circle means the function's not defined. So we can't plug in the number there because the function's not defined there. So the first thing that you need to have is you need to have the function be defined at that point. So in order to be continuous, the first thing you need is the function has to be defined at that point. Next one, I want you to look at C2. If you look from C2, we have one y value as we come from the left, the limit from the left, and we have a different y value as we come from the right. So the left and the right don't agree. If we plugged in the value, we would actually be given the limit from the left, but that is not the limit at that point. Remember, for the limit to exist, the left and the right must be the same. So we can't just plug in the value on this one. So the first qualification was the function must exist. The second qualification is the left and the right must be the same. So it must be the same from the left as it is on the right. When I'm talking about that, when I say it, I'm talking about the limit. So the limit must be the same on the left as it is on the right. And remember, if the limit on the left and the right are the same, that means the limit exists. So that's what we're getting at here, is what's the second qualification? That the limit must exist at that point. So the first thing, the function must exist at that point. The second thing, the limit must exist at that point. Let's look at the third one here at C3. At C3, there is a closed dot, so the function is defined. There is also the limit from the left and the limit from the right actually do agree, but the problem is the function value and the limit value aren't the same. So that's the third qualification. The function value and the limit value must be the same. So if we want this to be a quote-unquote nice function, where we just plug in the x value to get the limit and don't have to do anything else, we need the following three things to hold. The first one, the function must exist. So let me write that right next to it. The function must exist at that point. The second thing that you need is the limit must exist at that point. And the third thing you must need is the function and the limit must be the same. At that point. So those are the three things that we're looking for. The function must exist at that point, the limit must exist at that point, and those two things need to be the same. So if you were ever at a point where it says, is this function continuous or not? And you want to answer, no, it is not continuous, then you must cite one of those three reasons. Those are the only three reasons that you can cite to say a function's discontinuous. A lot of people like saying, oh, there's a hole, or there's a jump, or there's a gap. Those are not mathematical reasons as to why something would be discontinuous. The only three reasons that you can state as to why a function is not continuous, which is called discontinuous, at a point, is either the function doesn't exist at that x value, the limit doesn't exist at that x value, or that the function is not equal to the limit at that x value. It could be multiple things. It could be 2 or even 3. All 3 of those things are not true, but all you need is at least one of those things to be not true, and then the function is not continuous at that point. So now they talk about continuity on an interval, and I want to really highlight here that they always use open intervals when they're defining the intervals of continuity. You don't say the endpoints yet. We'll talk about can you use brackets later, but primarily we're going to be using parentheses. So what does it mean to be continuous on an interval? It just means that you're continuous at every point on that interval. And again, you have those 3 qualifications. Number 1 is the function exists at that point. Number 2 is the limit exists at that point. And number 3 is the function is equal to the limit at that point. And if it's continuous on every point on that interval, then that's the interval of continuity. So one thing, again, once again, it says, so to be continuous at a point, it needs to be defined, the limit needs to exist, and the function and the limit have to be the same. So very important that you memorize this definition. You are going to be asked to determine, is a function continuous at a point or not, yes or no. If the answer is yes, it has to meet all 3 criteria. If the answer is no, you have to state which one of the 3 criteria it does not meet. Okay, let's read this last paragraph. It says, to be continuous on the open interval AB, the function needs to be continuous on every point on that interval. When the problem asks for intervals of continuity, be sure to write your answer in interval notation. It is x values only, go from left to right. So again, a graph is only continuous if it meets these 3 criteria right here. But I do want to hint a little something here about graphically. How do you know if a function is continuous graphically? Well, the easiest way to know it is continuous if you can draw it without lifting your pencil. Again, it is continuous if you can draw it without lifting your pencil or pen. Okay? So an example of what would a continuous function look like, it would look something like this, where it's just a function, but you drew it without lifting your pencil. What would not be a continuous function? We've already seen in our list of basic functions. The function 1 over x, for instance, looks something like this. 1 over x is called the reciprocal function. This is not a continuous function because at x equals 0, when you look at x equals 0, you have a gap. It's a vertical asymptote, so that is not continuous everywhere. It would be discontinuous when x equals 0. So continuous functions, you can draw the entire function without lifting your pencil.